Okay, then, well, thank you first of all for inviting me here today. It looks like a very nice event, so I'm very pleased to join today. And the challenge I'll propose is a robust control design challenge, possibly to be solved via some available scenario, available realization of some uncertain quantities, and is an adaptation of an existing challenge, a benchmark control problem, quite old actually. So I also want to acknowledge two collaborators for that we worked on this challenge together before. So the problem statement is the following. So the available information we have are essentially two computational models. One is a model describing some other dynamic of a system, and a reliability model that essentially tells us how the system is performing under central condition in terms of certain reliability requirements. Furthermore, we also have a set of n independent experimental observation of certain uncertain quantities, delta, that are affecting the system response and reliability performance. So ideally, what we would like to do is to find a reliable design that maximizes somehow the probability of satisfactory performance, so essentially the reliability, but also avoids catastrophic failures. So somehow it guarantees certain degree of robustness against worst case scenarios. And differently from D, that is our design, these controllable random factors are just inherently stochastic and non-tunable. So if you look at the problem statement, maybe a bit better graphically, what we have is, again, a computational model that take as an input an uncertain scenario and a system design, and give us as output a response y over time. So this design vector is essentially a set of parameters we can control. Delta is a set of uncertain factor, and y is going to be discretized in time, at least in my code, but there's a set of differential equation that prescribe essentially this response for a given set of inputs. Of course, we have uncertainty in the quantity delta, so we might have very different dynamic responses when we change this quantity. On top of this system model, we have a reliability model. So essentially, the reliability model is telling us whether the system is performing safely or not. And this model takes the same input, so it's an uncertain scenario and a system design, and provides us output a vector of reliability performance function we call G. And in this example, we have two requirements. One is safe settling time, and we define it as safe, which is in this green area, and a safe control effort if the system response falls within this blue region. And by definition, we say that this reliability performance function is going to be lower than 0 and then is safe, otherwise greater than 0, and we are in a failure region. So in this example, for instance, we have a safe settling time, but an unsafe control effort. And if we have to plot the realization of the uncertainty in this G1, G2 diagram, we can see that we are safe in terms of G1, but unsafe in terms of G2. Clearly, we again have uncertainty, and potentially we have samples, but there's might be an underlying distribution actually that is generating our scenarios. We don't know that this underlying distribution. We just have a set of realization available to perhaps characterize this distribution or this set. And ideally, we would like to push the realization of the uncertainty. So find a design D star that essentially brings those realization of the reliability performance function as close as we can to the safe region, possibly fully contain the safe region, or at least not falling in very deep regions of the failure domain, which are known to be catastrophic in terms of failure. So in terms of metrics that are generally used to kind of compare design in terms of robustness and reliability, there are different ways to do this. One thing we did in the past is to use the worst case performance score, that is just the maximum of those reliability scores over the reliability requirement we consider, and we can eventually plot the empirical cumulative distribution function of this W, consider other metrics such as the worst case scenario score if we just consider the n scenarios in our data set, either for individual requirements or requirements. And this essentially, if for instance we look at the worst case scenario scores W, this is going to be the maximum of our W's in the data set. Another metrics we can use is the failure probability, or 1 minus the failure probability that is defined as the reliability, and looking at the empirical cumulative distribution function. The failure probability for a requirement here will be just defined by the intercept of the empirical CDF with the 0, in this case, 1 minus this value actually. Another thing we can look at if you're interested in understanding robustness or severity is look at the tail expectation of this distribution. And for instance, if you look at the definition here, is just the expectation of W in the failure region, conditional to the W being the failure region. So it's essentially, it's a quantifier of how deep this distribution falls in the failure region. So going into the challenge, so this is the kind of abstract setup, and the challenge specifically deals with a relatively simple system. It's just a 2 mass spring system, and that the goal is to optimize the controller for this system from given data, try to verify that the design is reliable and robust. Perhaps we can consider some essentially reachability of the failure domain, or at least reachability of some areas of the failure domain that are known to be linked to severe failures. So there is a repository for this. I have both a MATLAB code and a Julia code that carry out the system analysis, and we can look at this later if we have few minutes left. But just to give you an overview, so the reliability model for this system has 3 requirements. So our reliability performance function G1 essentially defines somehow how stable is the system, if the combination of system and controller is stable. G2 is about setting time, essentially quantifies whether the mass, the position of the second mass falls between plus minus 0.1 from the original state after 15 seconds and after initial excitation of mass 1. And the control effort is essentially a requirement on the controller that essentially the control signal must fall between plus 1 minus 1. And actually note that the time requirements requires essentially simulating the time response of the system by numerical integration. And so we have a dynamic model, a simple dynamic model for this. It's essentially a state space model, and we also have a transfer function kind of representation of this canonical model. So the goal here is to optimize those coefficients A and B, which are essentially the coefficient of the system transfer function. So those are our design parameters defining our vector of design parameters, but we also have uncertain factors, specifically on the masses of the 2 bodies, on the coefficient of the string, and on time delay and control loop lag, which are affecting essentially the state space matrices. So if we look at the data set available for those uncertain quantities, there are 2 data sets. One consider large uncertainty and the other small uncertainty. We just have 1,000 realizations of those 6 uncertain factors. And also bounds are provided for each one of the parameters. So you can notice perhaps already that there are some non-trivial dependency structures between the uncertain quantities. So this maybe can be taken into account. Otherwise, ideally, if one can prescribe a design that is guaranteed to have a G function, a reliability function that is lower than 0 for any value within this set, then we are sure that the system is safe. Although from my experience, might be difficult or impossible to find a design that is actually satisfying this condition for this set. So from previous work, so this actually some result that we published in 2019. We tried different kind of given data optimization problem to prescribe different designs, and those are some of the results we can use as reference. And the four designs are a nominal design that was just provided to us, and SP1 D0. So this is a design that was obtained by minimizing the worst case scenario score. SP1 was obtained minimizing the 95th quantile of this W score distribution. And SP2 was actually obtained by minimizing the probability of failure for all requirements directly. So you can see the kind of performance score in the first 4 rows and the design parameters in the last rows. So one thing I want to point out is that, well, first of all, the nominal design was performing quite poorly in terms of probability of failure and also in terms of worst case score for the individual requirements. While when we were trying to minimize the worst case scenario score, we obtained actually a decent performance in terms of worst cases, but quite bad in terms of failure probability. And the other design also, we always ended up essentially with a compromise between severity of violations and reliability performance. So this may be one challenge here. Another thing to mention is if we look at the fourth design in a projected space, essentially on the x-axis you have the mass of the first body and the mass of the second body on the y-axis, and those are in white the samples provided to us, and in red we have the failure domain, and in blue the safe domain. You can see that the safe domain is essentially as both safe and failure domain are non-convex functions of delta and also of the design variables. So this maybe complicates further reachability analysis. So just to summarize quickly, so I think this challenge, although the system is relatively simple, presents some interesting challenges. One, I think I want to point out 3. So one is a value of information and uncertainty characterization challenge. So we have a certain amount of data, but how can we use it in the best way? Should we prescribe a model of the uncertainty? How to keep track of the available information in the data set, for instance? We just had 1,000 samples, plus there were some kind of dependency structure available. Then another challenge is a reliability and severity kind of quantification challenge, because essentially reliability requirements are competing in this, plus robustness and reliability, severity and reliability also compete. And finally, if we want to kind of carry out the analysis with some sort of reachability set, how to estimate the failure probability from a set-based characterization. And then also in terms of optimization, there's a challenge, because we have to essentially compromise between robustness and reliability in a way, and we need to identify an appropriate optimization program and objective function or constraint. So we want to minimize severity, reliability, worst cases, or a combination of these. And then finally, the probability is estimated by a sampling is a stepwise discontinuous function. So if you use it as an optimization objective function, that might make a gradient-based optimizer difficult to apply. So as I was mentioning, so these are a few references the original problem statement, our proposed solution to the challenge, a few other papers that deals with the reliability-based design optimization and risk-based design optimization or optimization of severity. And this is the essentially code I prepared for the challenge. Maybe just quickly, you can see that you can essentially, so those are the design parameters, the uncertain quantities, design parameters. There's a function that essentially compute the state, create the state space matrices, and there's a reliability function that takes as input a design and validation of uncertain factors that provide some scores and the response, the dynamic response of the system. So if we were to, for instance, compare the performance of the nominal design, so those are this is the performance of a nominal design. So those are the three requirements projected in a scatter plot. The red samples are the failure samples, with the blue are the one that leads to an acceptable performance. And if we have to look at if you want to look at the dynamic response of this design for the 1000 samples we considered, this is the picture. In red, we have all the realization of the uncertainty that led to an unsatisfactory performance. In comparison, if you look at the second design, so the one with the lowest failure probability, this is the results. You can see that essentially we push the samples closer to the safe region, but not quite all of them. And also in this case, we have, let's say, less cases where the system performance is unacceptable, but still quite a few. So this essentially concludes my talk. Thank you for listening. If you have any question, please go ahead.
Yes. Thank you very much, Roberto. As always, let's give the speaker a round of applause. And I took the liberty of putting the link of the repository in the hackathon channel in Discord, so people who are interested can start hacking your challenge right away. And hopefully you will find a lot of great ideas and solutions. We have time for 1-2 questions if someone has questions.
I can ask.
Yeah, please go ahead.
Hi, Roberto, very good talk. So when you're doing the scenario optimization, you're dependent on the samples, right? And so sample generation is going to be an important factor. So in some cases, the domains and the distribution can look very different. So how do you efficiently generate samples from, possibly disconnected sets and things like that?
Yes, okay. So for this, if we are talking about the way I tried to approach this challenge in the past, I actually didn't generate additional samples. So what we did is to just use the data that was provided to us, the 1000 samples, optimize as best as we could for those samples, and then later on, we prescribed some kind of statistical guarantees on the reliability given. So essentially using some kind of value of information approach, we try to say, okay, given this 1000 sample, we found the best design we could. As you saw, there was no way of bringing the probability of failure to 0. At least we didn't find it. But at least we say, okay, this is the lowest probability of failure we found. Given this 1000 sample, we are that confident that whatever number of samples you're going to generate from the same unknown data generating mechanism, the probability of failure is going to be contained in certain bounds. So that's the way we approached back then. I mean, another way could have been to kind of try to first characterize a joint probability distribution function in some way, but then also in that case.
So yeah, I mean, that is a problem, right? Because you're doing scenarios, so you could be highly biased in the scenarios. You have not seen the bad scenarios and you are getting this overconfidence that things are good. So is there anything in that world? I come from traditional robust control framework, really don't understand a whole lot about the scenario side, but question is there a way to say that, yeah, I'm confident, my confidence is based on the samples, but there is some information theoretic angles, and I'm not seeing these things in my samples. So if I could get one more sample, where would I get it from? Is there any work?
Okay, so it's, well, I guess you can, I mean, you can think about kind of allocating samples where you want, but then it's difficult to say what is the real underlying probability that these events might actually happen. So of course, this is like the view of a robust kind of approach. You say, okay, you just a larger space, as I was mentioning. I also presented some physical bounds. Those contains the samples that are larger than that, is an hypercube in the uncertainty.
Okay.
If you can find a design that is actually fully reliable in this set, then we are. I mean, it's great. We are safe. But if you can't, then you have to, I mean, rely kind of on a distribution and try to find perhaps the best design you can by kind of reducing the kind of the uncertainty space using your samples, maybe. But I mean, that's at least my view with. Let's say if you can carry out a robust design and be like on that domain I prescribed, then it's going to be like fantastic for this. Otherwise, maybe one can think about finding a domain that contains all the samples, for instance, and is still and guarantees that maybe the failure region is not reachable in this domain. And there are different ways one can think about approaching the challenge, I guess.
Yeah, it's a hard problem, but anyway, thanks. Thanks. It's a great talk. Thank you.